I did want to welcome everyone to the East Brunswick Astronomy Club meeting for June. We're meeting a little earlier than usual. Typically, we meet the third Thursday of the month, but due to scheduling and room availability, we moved it up to the 5th, so thank you all for coming. My name is Isaac Osoris. I'm the president of the club, and we have a couple of board members as well here. By all means, if you have any questions, feel free to ask, especially regarding the club meetings. But in typical fashion, we do like to start off with our mission statement, which essentially just says everyone is welcome to attend our club meetings. You don't have to have any astronomy-related experience to join. Some of the folks that have joined our meetings have looked through the telescope for the very first time with us and seen Jupiter and its moons or Saturn and its rings, and it's just fantastic to see that their faces light up when they get to see that through a telescope. And I actually did bring mine here today. And here's our agenda. We typically run through the same format, which is we'll have a speaker. Today we have Evan Lewis, who will talk to us about pulsars, which is very exciting. Then we'll do a conditions overview, talk about what it looks like outside, what there's to see, if we're able to see anything. Upcoming events. Then we open it up for open discussion, where we invite you to give us some feedback, talk about anything that you've seen, if you've taking the telescope outside, or any other astronomy-related event. And then, so long as the weather permits and the smoke permits as well, we'll go outside and take a look through the telescope. Sounds like a plan?
Yeah.
Excellent. So, with that said, today we do have Pulsars, Enigmatic Cosmic Lighthouses. This presentation is being given by Evan Lewis. He is a 6-year graduate student at West Virginia University, where he uses radio telescopes to take observations of pulsars. He spent over a year working in the WVU Planetarium, where he gave weekly public presentations, as well as tours for school field trips and other groups. So let's all welcome Evan.
Perfect, thank you. Perfect, all right, great. Hi everyone, I'm Evan. I was already introduced, but I'm a grad student at West Virginia University, and I spend my day using giant radio telescopes like that one to look at pulsars. Pulsars are the dead stellar remnants of stars that have reached the end of their lives and collapsed in supernova explosions. They are super, super cool. You can do a lot of really cool science with them. Today I'm going to tell you a bit about what pulsars are, where they come from, and the science we can do with them. As you can see, learning about pulsars means we have to learn about a lot of other things. We're going to have to talk a little bit about quantum physics, just a bit. We're going to talk about stars exploding. We're going to talk about supermagnets, ice skaters. There's a lot of ground to cover. So whenever I'm putting together one of these presentations, I spend all day, every day learning about pulsars. So I try to find some kind of framing to give people to get their solid ground. So one good place to start is with the discovery of the first pulsar. That was in 1967. But then, I get in my head and I'm like, oh, well, some people use pulsars to study general relativity. Einstein, super famous. Maybe, I start by talking about him. I don't know, he was at Princeton. You could keep making this argument and going further and further back, the first telescopes, et cetera. And I feel like one day I'm going to start one of these presentations like, okay, so 14 billion years ago, the universe was created. I feel like that's a little bit too much. So we're going to start by hopping back only 1,000 years and learning about where pulsars are born. Like I said, they are created in the aftermath of supernovae, which happens when stars bigger than our sun run out of the fuel that keeps them going, and gravity takes over and the star just instantly collapses on itself, creating one of the most powerful explosions we've ever seen in the universe. We actually have evidence of having observed supernovae like these up to 1,000 years ago. So what I'm showing here is a copy of a court record from a Chinese imperial court about 1,000 years ago. This is back, obviously, hundreds of years before we had telescopes, but when people were still tracking the movements of the stars and the planets through the sky, at that point, usually to be like, hey, are the peasants going to revolt? Is that neighboring kingdom going to invade? How are the stars moving? Are they doing anything weird? Maybe we can divine what's going to happen from the stars. And in this record from 1054, we have a pretty unique observation that a guest star appeared. It was visible during the day for up to 23 days. It was pale red. It was notable enough for people to mention it in multiple different records. And it was enigmatic. No one could really explain what had happened. It kind of showed up one day and then disappeared after like a month. This was actually a supernova. And we have actually tied back records from another civilization on the other end of the globe to about the same time. So these are remnants from the Chaco Canyon in present-day New Mexico. There was a civilization that was living here also around the 1000s. And there is a pictograph, which you can see in the bottom right. There's a hand kind of denoting that like this is a really important monument, and then a moon and this red pointed star-like thing. Now, some very smart astronomers with some very powerful computers have looked at all of the, records of where were we on Earth when this thing rose in the east, where would they have been relative to the rising and setting moon. And the supernova of 1054 has actually been traced to a pretty well-known nebula, the Crab Nebula. So this is one of the more famous stellar remnants. The pictures are false color, but they're still really pretty. Essentially, what you're seeing is all the gas and dust left over from when a star collapses and goes supernova. In the middle of the Crab Nebula is actually a pulsar, the Crab Pulsar. There are some optical images on the very far right. You can just see a tiny little white speck in the middle. One great thing about being an astronomer is that we use the objects we study as like benchmarks. So one great thing is that because the Crab Nebula is so famous and notable, people will give us like the brightness of other stars in crab units. So you'll be reading this like very serious astronomy paper, and then someone's like, yeah, this star is about 42 crabs, and you just kind of have to roll with it. Okay, so we learned about pulsars being born in supernova explosions. We have some historical records of us observing these supernova explosions without even really knowing what they were. Now that we have the benefit of science, what's going on? So stars are basically giant fusion reactors. They spend most of their lives burning hydrogen into helium in their cores. That fusion reaction creates heat and light and all the things that give us life on Earth that we love about stars. Larger and larger stars are able to fuse heavier and heavier elements, and if you look at the biggest stars that we've seen, this continues all the way up until iron. When you get stars that are that massive, that they've got just a core of iron at the center, iron's kind of special because you actually have to put more energy in to fuse it to something heavier than you get out. So what ends up happening in these most massive stars is you will get a core of iron kind of collecting at the center. And what happens next will depend on the mass of the star that began. Excuse me. So for the lowest mass stars, I know our sun seems pretty heavy, but it's actually on the low mass end of the scale. What's going to eventually happen is it will run out of the hydrogen that it uses to fuse into helium. It'll puff up a little bit, and then eventually it'll just kind of run out of steam, stop being so hot and bright, and cool off as a white dwarf. But if you get heavier stars, about 1.5 times the mass of our sun at the center, there is actually so much mass in there that the fusion reaction keeping the star up can't hold up against all that gravity. And that massive core of iron, bigger and heavier than our sun, collapses in an instant. And that is a supernova explosion. They are some of the most powerful forces on Earth. I want you to imagine something heavier and bigger than our entire sun collapsing down into a very small region very quickly. This is a simulation of what a supernova explosion might look like based on data from one of NASA's X-ray telescopes, I believe. So as you can see here, after that initial flash, all that material is getting heated and it's expanding. And so you have this kind of bubble of really hot expanding gas. And if you let that keep going, that's how you would end up with something like this Crab Nebula here. So going forward again, this is a cartoon that I love. It gives you kind of a sense of scale of how big supernovas are. If you can't read it, it says Which explosion is bigger? 100 trillion of the largest nuclear bomb ever made, a ball of TNT the size of Earth's orbit, or a supernova? The answer is a supernova is more powerful than all of these. So the birthplaces of pulsars are these really insane extreme environments where a sun collapses in on itself. And it's actually because of that collapse that makes neutron stars have such interesting properties and why I want to spend all my time studying them. So they're extraordinarily dense objects. The factoid that we like to throw around is that a teaspoon of neutron star material would weigh as much as Mount Everest. So in a neutron star, they are typically about 1.5 times the mass of our sun, but they've collapsed into an area about 10 kilometers across. So these are densities that are way beyond anything we've ever even gotten close to seeing on Earth. Now, of course, when all this material collapses, the neutron star is still the same material that was there before the collapse, right? Which means it has to hold on to all the same properties that it had before the collapse too. Things like, did it have a strong magnetic field? Was that stuff spinning it all? Supernovas are really extreme, but the properties of that matter before and after are gonna have to matter. That was a bad pun, sorry. So one byproduct of this really extreme collapse is that pulsars spin really, really fast. The fastest pulsar can spin faster than your kitchen blender, hundreds of times per second. And the reason for this is the same kind of principle that applies if you've ever seen an ice skater spinning around with their arms out kind of slowly, and as they pull their arms in, they're able to spin faster and faster and faster. Essentially, as you move that mass in towards the center, it takes less energy to turn it around, and so it can spin faster. So what you end up getting is a neutron star. Typically when they're born, they'll spin a couple times a second. The millisecond pulsars, the really special ones that spin hundreds of times a second, they're a little bit different, and we'll come back to that later. The other thing I mentioned was the magnetic field. That is the other property of neutron stars that makes them so wild and so worth investigating. Because people don't deal with the strength of magnetic fields every day, shocking, I know, I gave you some example values that you could use to get a feeling for how strong these things are. So we use a unit called a Tesla to measure the strength of a magnetic field. The magnets on your fridge are less than 1/100th of a Tesla. Something a bit stronger, like the magnetic fields in the solar loops, the coronal loops that form on the surface of the sun, those are a heck of a lot stronger, but still only about 1/10 of 1 Tesla. There is a superconducting magnet facility of some kind in China that's clearly taken a lot of time and effort to build. It's a very big scientific endeavor, and the strongest magnetic field that people have ever created on Earth is, I believe, about 44 Teslas. To give you a comparison, the magnetic field strength of a neutron star is somewhere between 1 million and 100 million Teslas. So we're talking about objects that are 1.5 to 2 times as heavy as our entire sun, compressed into the size of New York City, spinning multiple times a second. The most extreme, again, spin hundreds of times a second. And they have magnetic fields 1 million times stronger than anything we've created on Earth. I hope that gives you some reason to understand why these objects are so cool and give us an opportunity to study physics that we just can't recreate on Earth. You might be asking me, hey, I've never walked outside and looked at the sky and seen a pulsar. How do you know all this stuff? So to give you a bit of context, I'm going to turn back to 1967 and tell you about the discovery of the first pulsar. So this on the left is a picture of Jocelyn Bell Burnell. She was a grad student at Cambridge in the 60s, and that is her standing in front of, believe it or not, a radio telescope. Back in the day, they just had a bunch of wires and antennas and used that to pick up the radio waves from astronomical sources, but also at that time there was, even then, a lot of human-made interference. I think her project was to look for the radio emission coming from other galaxies or something like that. But as she's looking at the output from this telescope, which by the way was on paper chart that was written with a pen recorder as the paper rolled through the chart, she noticed that in one particular region of the sky, there was a source of pulsating emission. It was extraordinarily regular. The pulses were exactly 1.33 seconds apart. There was never any deviation. But most importantly, as the sky continued to move overhead, that signal moved with the sky. What that meant was it wasn't created by humans on Earth, because if it was, it wouldn't matter where you were looking on the sky, you'd still pick it up. So at this point, no one really knew what neutron stars were, so it's not like people were expecting pulsars to exist, it's just that no one had ever seen one. So she's looking at this source of regular emission, and her advisor's like, it's just interference, it's human-made, don't even worry about it, it's just a waste of time, it's gotta be human-made. There's no way something out in space could be pulsing that regularly. In fact, this signal was originally called LGM1 for Little Green Men 1, because people believed the only possible thing that could be so precise would be aliens. However, I believe within the next couple months, she found another source with a different rotational period somewhere else in the sky, so that confirmed that, yes, these have to be real objects in space. Now, this was the 1960s, and things were unfortunately a little different back then. So this was a pretty big deal in the scientific community. It was kind of confirmation that these neutron stars exist. And for this, her advisor got the Nobel Prize. So yeah, it's a bit of an unfortunate scenario. And thankfully, since the astronomy community has kind of recognized her contribution, but it was not great at the time. So this is our picture of what we have so far, a rotating neutron star. There are a couple things I want to point out here. In astronomy, we use a lot of pretty colors and pictures to get the point across. If I were able to take you on a shuttle bus to a pulsar, you would not be seeing basically any of these lines. These are just illustrated to kind of give you a point on what's going on. So as you can see, the pulsar is rotating, but it's also got these thin blue lines representing the magnetic field. The same way on Earth, we have Earth's magnetic field, a north pole and a south pole. You can take a compass and the needle will point towards the north pole. In the same way, pulsars have these really strong magnetic fields. And it turns out that a byproduct of taking something with a super, super strong magnetic field and spinning it really, really fast is you get these beams of radio waves that shoot out of either magnetic pole of the pulsar. So those kind of purple floaty bits, that's representing the radio waves that are coming out of the magnetic poles. As you can see in a lot of pulsars, the magnetic field's kind of tilted at an axis away from the sense that the pulsar rotates. So what that means is that as you're standing away looking at it on Earth, all you're getting is the periodic flash as the pulsar's radio beam ticks past your line of sight. So that's why we call them pulsars, for pulsating stars. It's kind of a confusing name because they're not actually pulsing. It's just the signal that we're getting looks a lot like a pulse, so it's easier to kind of describe them that way. So I talked a bit about the first pulsar being discovered using that weird dipole-looking thing in 1967. And since then, we've spent a bit of time making bigger and stronger radio telescopes. Usually, the bigger the telescope, the more sensitive, the dimmer things we can see. So there are a bunch of cool designs you can see in the bottom right. That's kind of the standard, the Green Bank radio telescope. Big dish where the radio waves will bounce off of that dish and into this little collecting arm up at the top. And that's where the signals actually get digitized and recorded on a computer. We also have the Arecibo Observatory in Puerto Rico, which worked using the same principle. But then you've got some other unique ones. This is the Very Large Array in New Mexico. And it's essentially one giant radio telescope that's split up into a bunch of smaller radio telescopes. And down here is CHIME, which is a funny-looking radio telescope, but I promise it is still a radio telescope. And that one is in Canada. So one of the cool things about radio astronomy is you get to work all over the world. And I mentioned the first pulsar was discovered in 1967. We've been a little bit busy since then. And now there have been over 3,300 pulsars that have been published. A lot of the ways that we discover new pulsars are through surveys. Essentially what we'll do is we'll take a radio telescope and just kind of scan the sky with it. Look for signals from things. We don't know what we're expecting, but we can expect that in certain regions, like the middle of our galaxy where there's a lot of stuff, there will probably be more pulsars, more stuff, more stars, more pulsars. So as you can see, some of these surveys have looked just in the very regions surrounding this flat middle line here, which represents the kind of two-dimensional plane of our galaxy. Although you'll also have some surveys which will just kind of point the telescope up at the sky, scan the whole sky visible to that telescope, and just kind of see what you can find. Another thing that makes pulsars really, really applicable for a lot of science, as I said, is that they're extraordinarily stable rotators. And to give you an example of that, what these astronomers have done is taken the radio emission from these pulsars and essentially turned them into sounds. I didn't test this, so I'm hoping it will. There we go. So these are real radio pulses from one of the earlier pulsars ever discovered. The first thing I want you to recognize is just how incredibly regular this rotation is. And the other thing I want you to notice is how every pulse is just a little bit different. They all have different shapes. They all have different brightnesses. No two pulses are exactly the same. So by looking at each one of these individual pulses, we can learn something a little bit different. So this pulsar is rotating, about 1.5 times every second. We can take, I think this one's good. The pulsar signal will appear after a few seconds, but you'll see roughly the same thing. That one's a little faster. Again, this is heavier than the mass of our sun. Right. And my favorite example is, I believe, this one, which spins over 11 times a second. So this is the real sound of a pulsar. I can't even move my finger that fast, but you get the idea. There's one more that I'm not going to play because this pulsar spins 174 times a second. So imagine a loud ringing sound. There you go, you got it. Perfect. Okay. And I mentioned that the rotation periods of these pulsars are really, really stable, and we can measure them really, really well. So one of the pulsars that I just showed you has a rotation period of exactly 0.005757 blah, 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 blah seconds. And they're remarkably stable. So this value is not going to change very much over time at all. If my advisor or any other science people were watching, they would be mad that I didn't put an error bar on this. So really quick, I'll just add that. That is how precisely we have measured the period of this pulsar down to, let's see, millionths or billionths, trillionths of a second, something absolutely absurd. Attoseconds, that one. So pulsars rival some of the best atomic clocks on the planet. Because they're very far away and their signals are moving through space, it's hard to use them like atomic clocks, but they are that precise. A lot of the science that we can do with pulsars actually depends on the fact that they're so stable. Essentially, what we want to do is figure out how that pulsar is changing over time. How is its rotation changing? How is its position through the sky changing? And by making a model of how all that stuff changes, you can do some crazy math to figure out what that would mean about when the pulses will arrive at Earth. So you have this model predicting, okay, the next pulse is going to arrive now, etc. And by looking over years and years at the patterns in that model versus the data that you actually take, that's how we learn all of these incredible things about pulsars. And I'm not going to go too much into the math. I'm going to spare all of you. All right, so I've told you a bit more about pulsar science and how they make really cool beams of radio emission. In the back half, all I want to do is kind of take you on a really quick, brief tour of some of the things you can do with pulsars. So using these incredible objects as tools to study astronomy and the structure of the galaxy as a whole. The first thing that matters for us is dispersion. So you've probably all seen prisms before. It turns out that all of the gas and dust and stuff between stars acts the same way for the beams coming from radio waves. So this animation, essentially what it's showing is a pulse from a pulsar. Imagine instead of red, green, blue light, it's the same thing. We're just looking at high, middle, low frequency of one pulse from a pulsar. As that pulse moves from the pulsar to us on Earth, it's got to pass through all the gas and dust and all that other stuff floating around in between the stars. All of that stuff will delay the light from that pulse, but the delay is different depending on what frequency that light is. What that means is that if we're on Earth and we look at one pulse from one pulsar at one time, we see this kind of characteristic sweep where the part of the pulse at higher frequencies will arrive before the part of the pulse at lower frequencies. And this kind of dispersion is usually a problem because if we're just kind of blindly looking for pulsars, we don't know how much that delay is going to be because it depends on how much stuff there is. So if we're just kind of blindly searching, we have no way of knowing, and we have to search any combination or amount of delay to try and add up to create these pulses. However, this also works in the reverse. So that dispersion is usually an issue, but by working backwards with independent measurements of a distance to a pulsar, we can use our measurements of how much stuff is in between us and the pulsar and how far away it is to make models of the gas distribution of our entire galaxy, which I think is pretty cool. We're also able to use this dispersion to detect things from other galaxies. This isn't exactly pulsar related, but radio astronomy is one big happy family. So we use that dispersion or that delay to figure out how much stuff is in between us and the pulsar. But we have observed extraordinarily bright bursts of radiation that are so delayed there is literally not enough stuff in the Milky Way to have possibly caused that delay. What that means is that these pulses of radio emission have to come from other galaxies. And these fast radio bursts are still like a really hot topic in astronomy. Some of them repeat and some of them don't. So there are a lot of competing theories to try to explain them. Usually you can't really explain all of them given just one theory. It's a really big, contentious topic, what these fast radio bursts are and where they come from, although I will tell you it's not aliens, so don't get any ideas. One of the cooler discoveries that's come from pulsars is the first planets outside of our solar system were actually discovered orbiting a pulsar. Again, because pulsars aren't stars the way we know them, life on one of these pulsar planets would not exactly be great. You're getting blasted by high energy radiation all day, every day. But yes, using that technique of tracking the rotation of the pulsar over years and years, what ends up happening is you're able to find very, very slight minor fluctuations that you wouldn't have been able to find otherwise and figure out where they're coming from. So in this case, looking at the arrival time of pulses from this one pulsar over 12 years, someone noticed, hey, there's this pattern on the order of 20 microseconds over the scale of 12 years that, these are our model's a little bit wrong, and it's a little bit wrong in this very predictable way. And it turns out we can do the math of what it would look like if another planet was orbiting this pulsar and how that would kind of wobble the pulsar in its orbit. And it turns out that it fits that delay perfectly. So using these observations of a pulsar, we're able to find these rocky planets that we can't even see with our eyes because they're just too dim and too far away. Another related topic are spider pulsars. So using that same method of looking at the difference in arrival time of these pulses, we can find pulsars which are in orbit around another companion star. The same kind of thing happens where the pulsar is in this orbit, and so it's moving around, and the signal gets delayed or advanced depending on that. These spider pulsars are in binaries with stars near the end of their life. So stars that are kind of puffing up, getting a little bigger, their fusion is starting to run out. And pulsars are so energetic, and they have this like extraordinary blasting wind of high energy radiation that they actually rip their companion star apart. And all of that material ends up kind of spiraling and orbiting around the pulsar. So when they were discovered in Australia, of course, they were named after a species of spider. There are redbacks and black widows, and both of them kill their mates afterwards. So I guess people thought that that would be an appropriate name for these pulsar systems in which they kill their companions. All right, there's one more topic I want to talk about. Super easy, super simple, pulsar timing arrays to detect gravitational waves. Let's just like break that down real quick. You might have heard of gravitational waves before. That might at least sound vaguely familiar. The 2-second explanation is Einstein's theory of general relativity says that space and time are connected in this fabric, space-time, and that mass, stuff, will affect that space-time. It will give it curvature. The heavier mass, the more curves there are. So if we were to model something like 2 black holes or 2 neutron stars or 2 super, super, super heavy things orbiting each other, general relativity has a prediction of what that would do to the space-time around it. As you can see, it makes these ripples in space-time. Those are what we call gravitational waves. If you've ever heard of LIGO, that's essentially what they're doing to try to find gravitational waves, is they have these 2 really long laser arms, and as a gravitational wave passes through the detector, those little ripples will affect the laser light coming in at the very end, and that will let you be able to determine that you've found a gravitational wave. Now, people are trying to do the same thing with pulsars just to find gravitational waves on a different scale. So LIGO is really good for finding things like 2 black holes smashing into each other. Very, very fast, very, very strong gravitational waves that are really closely spaced together. But we also want to get a picture on what's the background like. Outside of these like really, really super bright events, what about all of the other really slowly orbiting black holes that are still super far away from each other, but are still making these much slower, broader ripples in the space-time that we all live in? Well, we would need to build bigger and bigger laser arms to do that. LIGO is already, I think, 4 kilometers in one direction, and we're running out of space on Earth, basically. So some very smart astronomers said, hey, what if there were these really, really precise rotating atomic clocks spaced all throughout our galaxy that we could essentially use as a giant detector? So there is an international collaboration of people tracking pulsars all over the sky to try to look for ripples in space-time as they pass in between us and all of these pulsars. As I said, this is an international collaboration. So I'm a member of NanoGrav, which is the North American nanohertz observatory for gravitational waves. But there are also European pulsar timing arrays, Chinese, Indian, South African, Australian, Indian, and I swear there's a Russian PTA that's also getting started up. And all of these have combined to form the International Pulsar Timing Array. So essentially using all of the pulsars scattered all across the universe, or at least in our galaxy, to detect these gravitational waves. All right, and to finish my presentation, I want to give you a little flavor on how pulsars have made their way into pop culture. If this image on the left doesn't look familiar to you, this is an album cover. I believe it's Unknown Pleasures by Joy Division. And it's just a really cool, nice piece of artwork, except it also happens to be an observation of individual pulses from the first pulsar ever discovered using the Arecibo telescope in Puerto Rico. So it's from this guy's PhD defense in the 70s. Essentially, you just take, a bunch of pulses and stack them on top of each other, and they make this really, really cool, beautiful mosaic, which pulsar astronomers do use to actually study how that emission is made and stuff. But I'd be lying if I didn't say that I would make these plots and then just kind of stare at them for a few minutes because it looks cool and space is cool. That's all the stuff that I had prepared, but I would love to answer any and all of your questions about pulsars. So thank you very, very, very much.
What a great job. Yes.
Go for it.
In that one where it showed the thing where it was the big line from the yeah. Why was the magnetic field? Why was it spinning? Why does it look like the magnetic field was spinning faster than the actual pulsar is?
That is a good question. So, I believe they're rotating at the same rate, but again, as you get farther away from the center, if you imagine two things rotating, as you get farther away from the center, it has to rotate faster and faster. So these magnetic field lines, they're still spinning, let's say this pulsar is rotating once a second, right? These lines are also spinning once a second. They're kind of attached to the pulsar, but because they're farther out, they have to spin faster, if that makes sense. They have to move in a line faster. Yeah, of course.
How bright is a pulsar?
That's a really good question. So I said that pulsars are these really extreme objects. It actually turns out they're not very bright. I might have an image somewhere, but it looks like I don't. So the comparison I've always heard is if you took a cell phone and were standing on the moon with the cell phone, beaming it towards Earth, that would be brighter than any pulsar we've ever seen. So pulsars actually aren't really, really bright. It's just that if we stare at them for really, really, really long times, then we can kind of add it all up to see them.
How long does the pulsar lines take to the Earth?
How long does it take to get from the pulsar to here?
Yep.
It's a good question. So most of the pulsars that we've seen are in our own galaxy. So they might take a couple hundred years to travel. What's the farthest one away? I could not tell you right now. But we can see pulsars on the other end of our galaxy. So it could take hundreds to thousands of years for that light to arrive. That's what's cool about astronomy is the farther away you look, the longer that light took to reach you. So it's the farther back you're looking in time.
For all the discussion about pulsars and their energy, it sounds like it has a extreme amount of it. Mm-hmm. If there is a way we could find a way to contain this energy, could we find a way to use the energy for our own purposes? Perhaps even with the ideology of space travel, or even if pulsar planets don't contain life, getting to planets that could be next to it that could contain it.
Okay, now you're engaging my technically, what if we could do this brain? Let me think. So pulsars do have a lot of energy, and a lot of it's stored in their rotation. Mm-hmm. It's like a truck barreling down a hill. You have something extraordinarily heavy, and it's spinning really fast. Mm-hmm. So all of its energy is in that motion. In order for us to take advantage of it, we would have to somehow get that energy out of the pulsar and get it in some kind of form that we'd be able to use it. That's hard because the neutron stars, especially at the surface, have extraordinarily strong gravity, right? So I don't know if we have the technology right now to build anything that could get close to a pulsar. And all the light that's coming from the pulsar is just a tiny fraction of the actual energy that's contained within it. They take thousands of years to give off even a small amount of that energy as radiation.
But in the future, could it be possible to get that energy? Could it be possible in the near future to create something that could contain it, or like could be able to be fathomed enough to contain it?
It's not physically impossible. I will give you that. It is. There's nothing stopping us in terms of like the laws of physics that we couldn't. It would just take an enormous amount of energy to be able to contain it.
And time.
And time. And the closest pulsars are still dozens to hundreds of light years away, so it would take us a while to get there.
Wow.
Okay, so I think you said you were from West Virginia?
Yes.
Yeah, I wondered what telescopes, like what's your home telescope, or which ones do you have access to?
So the best one that I used for most of my time was the Green Bank telescope, this one on the bottom right. That's in Green Bank, West Virginia. It's about 3.5 hours south of Morgantown, which is where WVU is. It's the world's largest fully steerable radio telescope. So that dish is able to pivot and look anywhere on the sky visible to it. The other one that I used a lot was Arecibo in the top right. Unfortunately, that collapsed a few years back. Yeah, very unfortunately, because a year before that was when my advisor was like, hey, we got this funding to work on this survey with data from Arecibo. You should submit a proposal to get more time on Arecibo. I submit this proposal. It's like, great, this is gonna go so awesome. And then like a year later, the telescope collapsed. So it's like, okay.
Well, time when these is precious, you have to put in a proposal and compete with other proposals, and then you get a window, and you better be there for your window.
Yeah, exactly. Especially Green Bank, I think people applied for 3 to 4 times, like as much time as there actually is. So yeah, there's regular proposal cycles, and you have to submit like technical and scientific justifications and lists of the exact amount of time that you need to observe and with what instruments, and then you cross your fingers and hope you get lucky and get that time.
And do you do it on site, or is it all remote these days?
It used to be all on site. Nowadays it's remote. So I was able in 2020, again, when they weren't inviting people to drive down to Green Bank, where the nearest hospital is an hour away, but they still wanted people to be able to get trained. They were able to do observer training, and you could just like remotely log into the computers at Green Bank and like open up the plotting software. And they have observers on site who handle the telescope side of it. Depending on your experience level, if you've worked with the telescope before, you can run your own observations or like give them the programming files. You can also just apply and have a project friend who's someone who is in your field but works at the observatory and says, okay, you want this mode, these settings, blah, 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 blah.
Okay, so first off, great socks.
Thank
That's
you very
awesome.
much. I thought they were fitting. They're NASA socks if you can't see them.
So two of my hobbies, one of course is astronomy, more specifically astrophotography.
Cool.
Second, amateur radio. I am painfully aware of just how much gunk we have splurted out into the sky. How do you deal with all of the interference that we generate?
By going to the middle of nowhere, essentially. I mentioned that Green Bank is in West Virginia. I've driven there a few times. You go to the edge of civilization and then drive over the mountain. Green Bank in particular is surrounded by actual like hills and mountains that's supposed to bounce a lot of it off. It's also in the National Radio Quiet Zone. There's also some military testing facility in the same region, but exactly. There have been times I've heard, this is, hearing from a friend of a friend, but You know, Green Bank astronomers are trying to study some signal. Oh, there's this really weird signal at this specific frequency. Hey, military testing folks, we're looking into this. Do you have any idea? Stop looking into that. Don't look into it. So yeah, most radio telescopes are in the middle of forests or deserts or places where there's as little human interference as possible.
How big is the biggest pulsar?
The biggest pulsar is as heavy as 2 of our sun, and I would say it's still about the size of New York City. So take our sun, get another version of our sun, and then cram it into Manhattan. And that's the biggest pulsar.
You have a question?
Since the pulsar is spinning so fast, does it ever move?
Does it ever move, like, in relation to us?
Like a top?
Yeah, well, all pulsars are spinning kind of like tops. The thing is, in space, there's not a lot of stuff to exert a force on the pulsar to make it move, right? If a pulsar is orbiting around something else, then it'll stay in that orbit the same way that the Earth orbits around the sun. But other than that, there's not much around that would impact a pulsar or get it to move off course, essentially. All of its energy is in its rotation, so that doesn't cause it to, like, move up, down, side to side, stuff like that.
Okay.
Any other questions?
So we can only detect pulsars when their beam runs across the Earth then, right?
Right.
So when we say we've discovered 3,000, however many it is, isn't it likely there are a great many more than that that we haven't discovered that are within our range, but we're just not picking up the signal?
Yes, there are, and there are papers which, do the math of beaming fractions, how wide are those beams? It varies from pulsar to pulsar. The inclination between the spin and the magnetic axis varies. So you'll have some that are like they're at 90 degrees to each other, and you'll have some where they're completely aligned, so you'll never see a pulse. So yes, population studies that do that kind of thing have to take all that into account. And there are also pulsars that over time have kind of expended all of their energy or don't have the energy to keep making that radiation. So there are probably a lot more neutron stars than the ones we see as radio pulsars today.
And why a neutron star instead of a black hole? Is it entirely dependent upon the initial mass?
Yes, so there is, and this is the quantum mechanics part that I skipped over because I took 1 semester of quantum mechanics and vowed not to take a second. Yeah, so stars are held up by that fusion, right? Once that fusion's gone, what holds white dwarfs and neutron stars up is quantum mechanics effects. It's electron degeneracy pressure and neutron degeneracy pressure. I can't explain them in intuitive ways because quantum mechanics isn't intuitive. Essentially, particles don't like to be in the same space. And so if you try to pack them really close, you have to overcome some threshold, and it's a mass threshold. So if there's enough stuff pushing down to overcome the electron degeneracy pressure, electrons don't want to be in the same space, then it can't form a white dwarf, it'll collapse into a neutron star. Then at about 2 solar masses, the neutrons not wanting to be in the same space will hold it up, but if it's heavier than that, then it will collapse straight into a black hole.
I heard something recently that there supposedly a big discovery of white dwarf pulsars.
Yes.
What makes them important?
So all of the things that I've told you and things we know about pulsars is that they are neutron stars, right? Like the beam of radio emission comes from the plasma outside the neutron star and charges are accelerated, et cetera, et cetera. In a white dwarf, it's bigger, the magnetic field is different, the situation right outside of it is different. So up until recently, we didn't think that white dwarfs could have the same kind of environment that would lead to these radio pulses. I do know what you're talking about, the white dwarf pulsar, and people are very much arguing over its emission mechanisms and what's causing it. Is it the exact same like physics? Is it the same idea, but in a slightly different configuration? That's what we don't know. And we only have one white dwarf pulsar and like 3,500 neutron star pulsars, so it makes it really unique.
Last call for questions.
So we've had a number of presenters that also had mentioned that there were opportunities for citizen science in their fields.
Yes.
Much like people like to take, my raw data from astrophotography can help visual observers. I remember there used to be, I don't even know if it's still running, SETI at Home was the program that you could donate your spare computer time to help. I don't know if it played into your world. Are there opportunities for citizen science in what you do?
It's so funny you mentioned SETI at Home, because I was just about to tell you about Einstein at Home, which is the same thing, but instead of processing SETI observations, it's taking observations of pulsars and, usually, let's say we're staring at a blank part of the sky and looking for periodic signals or looking for pulsar-like signals. We have to process them at a bunch of different a bunch of different ways. And Einstein at Home is doing exactly that with your spare CPU cycles, taking observations and searching them for these periodic signals so that we don't have to use supercomputer time to do that.
You've mentioned how pulsars create amount of radiation from them, and that any planet orbiting around them can, cause some negative effects. If there were to be a pulsar per se placed within our solar system, like in our current solar system, would that affect our entire planetary system?
Yeah. So, okay, the biggest problem would be that you're putting something heavier than our sun in our solar system. So that would mess up all of our orbits, first of all. If you just replaced our sun with a pulsar, let's say, I would have to do the math in my head really quick to, I'm trying to, I don't know exactly how much energy we'd be getting from Earth. The good news is that Earth's atmosphere is able to block a lot of other wavelengths of light from getting to us. We still have to deal with some, like UV radiation and stuff like that, but like X-rays and gamma rays, if astronomers want to study things in X-rays and gamma rays, we have to send satellites outside of Earth's atmosphere because all of that stuff gets in the way. So we'd probably get some interference, but I don't see the radio beam being an issue, except for the lack of actual sun. That might be an issue, but I don't think it would cause any problems.
I was just asking because I just know that pulsar waves do eventually come to Earth. So I don't know if they're extremely dangerous to us or if they affect us if said pulsar rays were to reach Earth. Would they have dulled down by time or would they still?
Yeah, so I mentioned that there is a wind of super energetic particles coming from the pulsar, especially at high energies. Luckily, they're only relevant if you're very, very, very close to the pulsar. If we were, again, the Earth-Sun distance, if you're 1 AU from a pulsar, let's just say it wouldn't be great. I can't imagine it would be great.
Well, it's something to imagine. I mean, pulsars can be created, especially with our stars, slowly being born and dying and then, supernovas and such.
Yeah.
I mean, one of our stars could be a blue star for all we know, near our solar system. So it's something to, constantly think about in case it ever occurs, you know?
That's why we keep looking for new things.
That's awesome to hear.
Awesome. Last call for questions. Not seeing any. Can we give Evan Lewis a huge round of applause, please?
Thank you. Thank you.
All right. I do use Astrospheric to look at the conditions and see what they will be for the time that we meet. This is what it said it would look like. It does look a little hazy outside, but we'll still go outside and see if it's still looked that way. If not, then we have the telescopes and we'll do the best that we can, but no promises. In typical fashion to our club meetings, a screenshot of Stellarium, which is the app that is available on the web as well as on your cell phone, just to see what would be out there tonight. So we have the moon and Mars as well as a couple other things. But in the video, it did show the different phases of the moon, with June 11th being the full moon, the strawberry moon, this month. And also in typical fashion, we like to promote the different UACNJ events. Is anyone familiar with the United Astronomy Clubs of New Jersey? Couple nods. Great. So since they've opened up for the season, they hold free weekly events every Saturday night at their location up in Jenny Jump State Forest, where they have about 6 or so observatories that are free and open to the public. Similar format to what we have. They'll have a presenter talk about a specific topic. The 7th of June will be What's Up in a June Sky, given by Lonnie Bunis. And then on the 14th, The Beauty of the Universe. So, and it's every week, every Saturday evening. So if you're ever free on a Saturday night, feel free to take a trip out to Jenny Jump State Forest. It's a great place, especially if the skies are clear. You'd be surprised how many things you can see just stepping out of the car, just because it's near the Pennsylvania border, away from a lot of the light pollution. It's a really nice facility. And then, of course, we have our next month's meeting, which will happen on the third Thursday of the month on July 17th. And I'm actually going to invite Christy, our VP of Engagement, to talk about our next meeting.
Hi, everyone. So I'm Christy. This is my son, Kevin.
Hi.
So Kevin is one of our youngest members and will be returning to present again for those of us who were here in March. You saw us talking about the Mars rover, the Mars rovers with the Robotics Club, and next month we'll be back to talk about Venus and the greenhouse gases. We'll also be joined by the East Brunswick Sustainability Task Force to talk about greenhouse gases here on Earth and do some sustainability crafts for kids, so we can take care of our atmosphere here at home, and also try to get the kids outside with the telescopes as well. So if you, it is for children of all ages, including big kids. So if you have little ones who would love to see also a child presenter that maybe they identify with, as well as adult presenters, feel free. It'll be a night for the whole family.
Yeah, so definitely save the date. Our last...
It's earlier.
Yes, so it does start at 6:30, so a little earlier than our typical start time. But that'll give us a chance to have Kevin present for us and go through the different activities that will be there. So definitely save the date. And shameless plug slide. So if you're not following us on Facebook or Instagram,
The quick fire presentation is no one's on yet.
it's coming up. Yep. If you're not following us on Facebook or Instagram, please do. It's the best way to keep in touch with us, stay updated. Just like today is not our typical meeting time. Typically, it's the third Thursday. But we advertise it on Facebook and Instagram, as well as our website, which is very easy to remember, ebastro.org. Thanks, Paul. No, you're good. So as Melissa mentioned, we do have a what we like to call the quickfire presentation for our August meeting. And for this one, we're inviting all of you to see if you have an interest to give a quick presentation on an astronomy-related topic. So no pressure. We're a very welcoming group, as you probably experienced today. But you know, it's a great opportunity to come up and speak to an astronomy-related topic, 5 to 10 minutes. If it's less than that, that's fine too. But just give other folks a chance to come up here and speak besides myself. So there's a QR code as well as a link to the form to show your interest, or you could just email us at info@ebastro.org and let us know that you're interested, and we'll be happy to slot you for our August meeting. It's a nice change of pace, right? Because typically we have great presenters come and give us a talk on something very interesting, but how great would it be to hear from one of your own sitting in the seats here? So it's a great opportunity, a great chance to just give a quick public talk. So a couple other slides, such as, did you know this club is actually an associate club of the United Astronomy Clubs of New Jersey. What this means for you all is that you can sign up to become an observer member at UACNJ, which is awesome. It comes with a lot of perks where you get access to the facility up there. There's a house. You would get the access codes and access to the observatories as well once you get signed off. Plus, you get to volunteer there and help out during their weekly meetings. So if that is something of interest to you, by all means, check out uacnj.org. They have a membership page where you can read a little bit more about what that entails, but it's a great perk if you're interested in astronomy and using some of their equipment that they have up there. And then another brag slide, I guess. This club has recently been added to NASA's Night Sky Network, which is great for us. It allows anyone who's going on their website to look for an astronomy club that's near to them. They'll find our club if they're within our range and tell them a little bit about our club, show them our website, events. There's even a request an event and a contact club tab on there as well. So it's really great for us. We're a very new club, but to have that exposure is excellent. So with that all said, tell your friends, and hopefully we continue to see our attendance continue in this nice trend that we have. Thank you all for attending. Thank you.